So today I'll talk about how to prove this statement. So if n is an integer and n is even if and only if n squared is even. So from the statement if and only if if and only if, we can tell that this is a biconditional statement. And then we write biconditional statement like this, right? That's biconditional statement. And how do we prove it? If we want to prove a biconditional statement, we need to prove two things. We have to make sure this is true, and we have to make sure another way is also true. We have to prove both these and these are true. So that's before we start. I think we need to know two definitions. So an integer number x is even if and only if there exists an integer y such that x equals to 2y. And the second definition is an integer number x is odd if and only if there exists an integer y such that x equals to 2y plus 1. Okay, now we can start. So first let's prove this. P and this. P is a hypothesis and the Q is conclusion. So here P would be, in this statement P would be n is even, and Q would be n squared is even. Like they're integer, right? Okay, and then so if we want to prove this, here we can simply use direct proof. And what is direct proof? So basically direct proof is we assume hypothesis is true and we use this P to show conclusion Q is true. Yeah, that's direct proof. So n is even. So from the definition 1, that means there exists an integer k such that n is equal to 2k, right? So now we need to prove n squared is even. So n squared is equal to this. We do some algebra, and we keep doing it. We can make it like this, right? So we know that integers are closed under multiplication. So this one is just, the result is also an integer. So yeah, so n squared is equal to 2 times the integer. That means n squared is an even integer, right? Yeah, we just proved it. So we proved this one. Now we're gonna prove this. So here, if we prove it, if we want to use direct proof, it's a little bit hard because it's not that straightforward. You see, like n squared is let's say n squared is even integer, right? I'm going to show n is also an even integer. That means this equal to n equal to even integer. It's not that easy, as you can see, right? Not that easy. So when direct proof is not working, it works, but when it's hard to do direct proof, we can always use contrapositive. So what is contrapositive? Basically, this is contrapositive. Q. This, just wrote it again. This is equal to this. they are equivalent. So this is called contrapositive. So we reverse P, we put it here, and then we reverse Q, and we put it here. Yeah. Okay, now let's prove it. So reverse of P would be, we see P here is N is even. That means reverse of P is N is odd. N is odd. Reverse of Q, we try to show N squared is odd. Okay. From the definition 2, we know if N is odd, that means N there exists integer k such that 2k plus 1 equals to N. So we do N squared is equal to 2k plus 1 squared, and then we do some algebra. We can simplify it more here. And then from here, we know that integers are closed under multiplication and addition, right? So we can tell this part, the result would be an integer. So yeah, so from the definition 2, we can tell this part shows that N squared is also odd. So N squared is odd. Yeah, so now we just prove this using contrapositive here. Now we proved both of these are true, so and that's it. And we prove this by conditional statement is true. Thank you.